Hi, welcome to another episode of Ordinary Differential Equations. Today we are going to continue our conversation about direction field. I'm going to solve two problems related to this topic. So, problem one is a simple question. Consider a differential equation y prime is equal to y minus 2 times y minus 4 times y minus 6. Find equilibrium solutions and label them as stable or unstable. Let's go ahead and do this thing first by hand, and then also double check our solution with respect to that software we talked about in the previous lecture, D-field software. And then we'll see another example in another problem that I'm going to talk at the end of this lecture. So equilibrium solution, we said that means y is not changing, therefore y prime is going to be 0. If I set the right hand side equal to 0, conveniently all the items are factored for me, so I'm not going to struggle that much to find out that I have 3 equilibrium solutions. The question is, how do we decide which one of them is stable or unstable? There are several ways to approach this. One of them is by looking at that phase plane that we had, that is, draw the direction field, as much of it as necessary. So here I draw the coordinate system, y, let's consider let's say 2. So this is 1, 2, 3, 4, and 6. So my equilibrium solutions, one of them is this one, the other is this one, and the third one is this. So y equal to 2, y equal to 4, y equal to 6 are equilibrium solutions, meaning if I start on this line, then on the right hand side y equal to 6, that makes this 0, y prime is 0, therefore my progress is going to be as x moves, y stays stationary. And if I repeat it again, I will be going forward in these lines. I neither go up or down. So these are all equilibrium solutions. The question is, well, what about other points? These 3 lines are going to divide the plane into region 1, 2, 3, 4, and we want to decide what happens if you start anywhere between these lines. So let's start from the very top. If I am here above 6, so if my y is larger than 6, then all 3 factors are going to be positive. Therefore y prime is positive. That means at this point I'll be moving up. I didn't carefully calculate the number. I just need to know if I'm moving up or down. Now suppose I pick a point between 4 and 6. Could conveniently pick up 5, but any number between 4 and 6 would do the same job for us. So pick a number between 4 and 6. Well, then y minus 6 will be negative, but these two will be positive. So in this region, y prime is negative. That means I'll be moving downward. Between 2 and 4, so if I pick a y value between 2 and 4, then y minus 6 is negative, y minus 4 is negative, but y minus 2 is positive. So I have positive times negative, so my slope is positive. It means I am moving up. By the same discussion, if I pick y less than 2, then all three factors will be negative, and therefore my y prime will be negative, and I'll be moving down. So that is enough information for us to decide what happens as we move to higher values of y. This slope is going to rise and become higher and higher values. That means my solution is going to look like this. If I come close to 6, this factor is close to 0, the product is close to 0 but positive. That accounts for this tail that looks in this fashion. If I've chosen a number between 4 and 6, then this factor is negative and the other two are positive. So my y prime is negative. I am always descending. I'm descending, but as I come close to 4, this factor makes the product to be close to 0. Negative but close to 0. So I'll be acting this way. If I go toward the negative x values, I'll be approaching y equals 6. Notice that during this entire picture, the y prime is negative. The story for a number between 2 and 4 is flip image of that. Between 2 and 4, my y prime is positive because these two are negative and this is positive. Positive, negative, negative is positive. So this slope is positive. I go up, but as I get close to number 4, this factor makes the product to become close to 0. As a result, I'll dampen out and I approach 0. If I go toward the negative axis, so what happens is that, the slope is always positive, but now coming close to 2, the product becomes 0 because y minus 2 becomes close to 0. Finally, if y is less than 2, all three factors are negative, therefore y prime is negative, and therefore I am always descending. Nothing is holding me back. If I go toward large negative x's, what happens is that this factor is making the product close to 0 while it's being negative. That makes my picture to flatten out in this fashion. So you can draw several other trajectories quickly. It's essentially same as these pictures you have already drawn, but move to the right or left. So I can draw another one, for example, here, or I can draw another one here, and another one here, and so on. So let's draw another one for good measure here as well. They always stay apart from each other. So we notice that around y equal to 4, all the trajectories come close to 4. That makes this to be stable. But around y equal to 6, if you step away from 6, you are either pushed all the way to plus infinity, or you are sent to another stable solution, which is 4. So this one is going to be labeled as unstable. Another terminology for this thing is that this is an attractor. This is a repellent. This is like a line that's attracting these other lines into itself, while this one is repelling everybody. All the lines move away from it. Same way here. This is also unstable, or you can call it repellent. So we could figure out what the solution of this thing is going to look like quickly by ourselves. Let's just go ahead and verify that we are on the right track. So I'll go and enter my right hand side of the equation, y minus 2 times y minus 4 times y minus 6. I mistyped. This is a y, and this is supposed to be minus, not underscore. My independent variable, I can call it anything. I need to include y equal to 6 in my picture, This is not high enough, so I might as well go a little bit higher than 6. So maybe, for example, 8 is good. Now I go ahead and draw my picture. So you choose your window so that it includes points of interest. Now let's go ahead and see. So we said the critical marks are 2, 4, and 6 as expected. You can notice that across from 2 the direction of arrow flips same way across 4 and same way across 6. But to be sure, pick a point under 2. Notice it descends very quickly. Pick a point between 2 and 4. Here's another example. You notice that they are all same curve, it just moved to the right or left. Pick a point between 4 and 6. That convinces us. And pick a point above 6. So notice that everybody's running away from 6, so 6 unstable. Everybody's getting attracted to 4, so 4 is stable. Everybody's running away from 2, so 2 is unstable. So unstable, unstable, and in the middle, in this case, we have stable solution. Notice that we could get the same answer ourselves without resorting to the software, and that's what you should do anytime. If it is possible for you to work it out yourself, then you should go in that direction. Okay, for next problem, something a little bit more involved and a little bit more algebra, and type of problem that shows up in several homework problems. So let's go ahead and get that started. So we have so solve y prime minus 3y is equal to 5 minus 2t, subject to the initial condition that y of 0 is equal to some number k. Now the problem might be posed in a rather ambiguous type of question. It might be asked that you discuss long-term behavior of y in terms of k. Well, what do we mean by long-term behavior? What does it mean in terms of k? Two ways to explain that. One is, well, let's go to that software and see what do various solutions look like, and then we come back and rephrase this question in another style. So we go back to our favorite software here, D-Field. I pick, I need to put the right hand side the way it shows here. So it has to be y prime is equal to something, so I need to take this 3y to the right hand side. So I write 3y. In this software, writing 3y, it understands that you mean 3 times y. As a good practice, you want to actually include a multiplication sign. So just to be correct, I did that. Minus 2t. So it is red. What should I do to correct it? Did you figure it out? So it's already giving you an error message. T is unrecognized function. Your independent variable has to be t. So you have to be consistent. Whatever, if you're using x here, this has to be x. If you're using t here, this has to be t. And we have some window. Let's go ahead and try it, see if that's good enough. Otherwise, we come back. So this is the direction field. Let's click in a few places to see what happens. We already see that here everybody's going up. Down here it looks like things are going down quickly. So let's go ahead and pick some trajectories up here, some trajectories down here. So long-term behavior. Here are different kind of solutions. Obviously, a group goes up, another group goes down. So that's a clear distinction between the behavior of two groups. We want to know what is distinguishing one group from the other. There are some places, if you click here, you go down. Some places here, you click and you go up. The way it's phrased is that y of 0 is equal to k, meaning take t equal to 0. So in this entire line is when t is equal to 0. K is the point in this line that you are choosing. So for example, if I choose this, it means I've taken k equal to minus 2. K minus 2 has the fate that it goes to minus infinity. While if I had taken k equal to minus 1, it goes to plus infinity. So obviously somewhere between minus 1 and minus 2, the fate is changing. Well, where is it that is flipping over? It is somewhere here. It's kind of, you can eyeball it and say, well, it looks like almost like minus 1.5 or something around that. So if I'm above it, I go to infinity. If I'm below it, I go to minus infinity. The question is, well, can you figure out where that separation point is? At what value is it that we are separating these two groups? So you can do it two ways. One, experimentally, you can expand this and then try and try and try different points until you hit the right spot. Well, that's going to take a lot of patience, but sometimes that's the only way you can do it. And if you're lucky, maybe you can solve the equation and then figure out what is causing the two different behaviors here. So that's what it means, long-term behavior in terms of k. So what point should I click that I go up versus what point should I click that I go down? There's exactly one value in between that separates these two groups, and that's what you want to find. So rephrasing this question, you can ask it like that: find values of k for which limit of the solution as t goes to infinity is plus infinity, versus values of k for which this limit becomes what? Our point of distinction was one group goes up, another group goes down. Can you tell at what point does this happen? So again, you can experimentally click and click and click until you figure out what k is. And the other one is, well, actually solve the problem if possible and then decide that way. Let's go and solve it. Well, we look at this thing and say it falls in a certain category of equation we studied before. Let me ask everybody to think about how would you approach this equation. How do you solve it? In fact, you should be ready to solve this thing and give me the exact solution in a few minutes, like maybe 5 or 6 minutes. You should be able to produce the solution. So this is an excellent spot for you to stop. I mean, for me to stop, and for you to actually get your pencil and paper and go after this. So here's our a nice picture. You look at that for a few seconds, settle down, and hopefully that energizes you to get the solution. So I proceed to find it. At various points, try to stop the video, cross-check your answer against what I'm obtaining, and see if you have any error, correct it. Hopefully you go all the way to the end and you don't need me. Let's go back to the lecture. Okay, so you are working it and then coming back. So the method of solution. First of all, what method applies here? Well, it's a linear equation. It's not separable. The only thing that I can think of is the method of integrating factor. Integrating factor, we need our leading coefficient to be 1. Thankfully, that is already 1. Our integrating factor, m or mu, is exponential of integral of this, the function that's multiplying y, is exponential of integral of minus 3 dt, which is obviously exponential of minus 3t. In this case, carrying a constant around with you doesn't do any particular benefit to us, so that's we pick exponential of minus 3t. I multiply both sides with that, so I'll have y prime exponential of minus 3t minus 3 exponential of minus 3ty. Right hand side is 5 exponential of minus 3t minus 2t exponential of minus 3t. Next, I verified the left hand side, in fact, complete derivative of a product y3t prime. If I differentiated y prime times second function, derivative of the second function times the first function, and right hand side I have this expression. Now I integrate both sides, so save a little bit of time by just putting the integration sign here. So I am integrating, of course, I should write a dt here and dt here, but that is implicit in what we are doing. Integral of a derivative is just going to be the function itself, y exponential of minus 3t. Here I'm going to calculate these two antiderivatives, and at the end I'm going to add a constant here. The first item is easy, 5 exponential of minus 3t over minus 3. This one is an example of integration by parts. You can just do it the ordinary way. We also had a shortcut. You can apply any of those. I'm going to just do it the same way that you have done this in calculus. First, I concentrate on this, and then I multiply by minus 2 later on, and then put my constant at the very end. So the question is t exponential of minus 3t dt. How do you do that? So what you want to do again is to stop at this level, make sure up to here you are all correct, and then pause this video, do this integration by part. You should be able to do that in a matter of 1 minute at most. This is standard integral, so we are going to use u dv is equal to uv minus integral of v du. So let's write the ingredients here. My u is going to be t, and dv is whatever is left over, so exponential of minus 3t dt. If u is t, then du is of course just dt, and if dv dt is that, then v has to be exponential of minus 3t over minus 3. So this integral is going to be u times v, so u times v, that's going to be t exponential of minus 3t over minus 3. So this uv is that, minus v du minus v is this expression, du, which is now our dt. So I clean this up one more round. So I'll have t exponential of minus 3t over minus 3. Minus and minus going to be plus. I have to divide by another factor of minus 3. So that's going to become minus again. Minus exponential of minus 3 to divide by another 3. This makes it 9. Okay, so that's the antiderivative of this. subject to a constant, I'm going to double this and then throw in a constant for good measure. So this becomes minus 2 times this expression. So that 2 was left out. I'm bringing it in now. And then I can put my constant. Just make sure that you don't mix up your constant. This one was a K, and this one, any other letter would do. So for example, a C is good as anything. So we did some side calculation here. I put the side calculation on a side mark so that things do not run into each other. So sorry. So let's go ahead and clean up our expression here. So I have y exponential of minus 3t. That's equal to minus 5/3 of exponential of minus 3t multiplied by minus 2. So it becomes plus 2/3 of t exponential minus 3t. And this becomes plus 2/9 of exponential of minus 3t and a constant. I might as well combine these two. So y exponential of minus 3t is equal to, I have minus 5/3 plus 2/9 of exponential of minus 3t plus 2/3 of t exponential minus 3t and a constant. Now we go ahead and take care of this one. So that is common denominator 9. It becomes minus 15 plus 2. So that's minus 13. And I have my other pieces written out one more time. So I'll have now almost the solution. I go ahead and multiply by exponential of 3t so that it all cleans up. So I'll have y is equal to, when I multiply by that, this expression just becomes minus 39. This becomes 2/3 of t, and then the constant times exponential of 3t. So that constant is very important here. So this is y of t. Now we want to focus on the point where t is equal to 0. That's where our initial condition is given at t equal to 0. At t equal to 0, my y is supposed to be k. So I go ahead. So y of 0, that is minus 13/9. This is 0. And c exponential of 0, well, that's just 1. All of that is supposed, y of 0 is supposed to be k. So that tells me that c, this is 1, this is 0, c is k plus 13/9. So our final solution then is the following. Y of t is equal to minus 13/9 plus 2/3 of t plus k plus 13/9 of exponential of 3t. That is the solution. Solution of the differential equation that we were given is this. Okay. How can I use this to answer the question? What's the long-term behavior? So long-term behavior is the limit of y as t goes to infinity. All we want to know is that are we going to be positive infinity or minus infinity? Well, what's happening? This t goes to infinity, yes, but so does exponential of 3t. However, this infinity, you know from calculus 1, this infinity is a much bigger than this infinity. So when t goes to infinity, the dominant factor is this. Now, if the coefficient in front of it is a positive coefficient, we go to positive infinity. If it's a negative coefficient, we go to negative infinity. If this is 0, everything's going to be delegated to what this one is doing. So let's decide the cases. If k plus 13/9 is positive, then I have positive infinity dominating everything else. My limit is plus infinity. If k plus 13/9 is negative, if this is negative, it doesn't matter what this factor is doing, because exponential is much bigger than linear. So this is going to decide that we are going to go to minus infinity. However, if k plus 13/9 is exactly 0, if this is 0, if we manage to keep this thing as a 0, everything is going to be decided by this. And this one, when t goes to infinity, that goes to plus infinity. So our final statement is the following. If k is larger than or equal to minus 13/9, then y goes to plus infinity. If k is less than 13/9, so I set this thing equal to 0, I'll figure out k is minus 13/9. Then y tends to minus infinity. Set of initial values that we go to plus infinity is this. Instead of initial values that goes to minus infinity is that. Let's go ahead and verify with our picture that we are on the right track. So this was t equal to 0. So what we have discovered is that that exact point is minus 13/9. 13/9, well, what is 13/9? 13/9, you just divide it out, 1.444, etc. So the crucial point is minus 1.444. So let's go play with that and see if that's actually correct. So let's draw this thing one more time. So everything's erased. We start again. We are on this line, and we said this is a situations where you click is going to be significant, so you might as well do it precisely. If you want to do it by hand, well, yes, we know at -1 we go up, at -2 we go down. But where is the breakpoint? The breakpoint, I typed it before this started. Let's play with it. Suppose I started at -1.4. You see, we were getting pulled up. -4.4, we are still going up, but we take a time to go up. This, we are getting closer to the critical point, so it takes a longer time to go up, and so on. Even with so many 4s, we still see. So to stay on that line precisely forever, this has to be precisely minus 13/9. You notice that even after 2, 4, 6, 8 digits, we are still going to a certain direction. So if you want to stay exactly on that line, you need to start at -13/9. Now, in this equation, some more discussion of this. This portion of it is called the asymptote of the solution. This is the equation of a line. That's exactly the line that you see here. This line, everybody's crowding around this line, is the one that we saw in this expression, -13/9 plus 2/3 of t. That is exactly what that expression is. Here, let's draw a few down here so that you see there are actually two groups of solutions. These are all the ones that are going to minus infinity. This is the value of the k that you are choosing. So if my k is like -3, I'm being pulled down. If my k is say 0, 1, and so on, I'm being pulled up. Okay, that was an example of an elaborate question on long-term behavior. We did it by theory and integrating factor method, discussing the solution like that. We also saw the advantage of the software. It gave us a pretty good answer by just eyeballing it, but to get the precise answer, we needed the exact solution. Okay, thank you for staying on, and we are going to have more questions related to direction field coming up, but we are going to have also a very nice section on applications of linear equations, and this is going to take us quite a while to go through. Okay, until the next lecture, good luck and God bless.